Okay, this is checkpoint 2. Still some more on gravitational fields, but we're also trying to combine this into circular motion and talk about Kepler's Law, which is officially not on the specification, but it does come up quite often. So here's two planets, P and Q, of different radii and different densities, and it tells us that P has got a gravity of 13.4 newtons per kilogram. So we need to look and do this by ratios really. So this is P, it's got a radius and a density. This is Q, it's a bit more circular than that I'm sure. It's got a radius that's twice as much and a density that's half as much. Okay, so as you might remember from the last one, if we talk about surface gravity, that's gm over r squared, but because we're doing a density here, that becomes g times 4/3 pi r cubed, that's the volume, rho for the density, divided by r squared. So the r's on the bottom cancel out with 2 of the r's on the top, and we end up with g equals 4/3 g pi r rho. So what we've done here is double the radius and half the density, so we end up with the same surface gravity. So the answer is B. Okay, this is quite a tricky one I think. So this is a planet with x times the radius of the Earth, and the surface gravity is y times as big, and we want a ratio of the masses. So the way to do this I think is to talk about the gravity on the Earth is g times the mass of the Earth over the radius of the Earth squared, and then on our new planet the gravity is y times as strong, so yg is g times the new mass, okay, which I'm going to call m dash, divided by the new radius, but the new radius x times as big, so that's xr all squared. Once you've written those two down, it might not seem particularly obvious where to go, but we need to get to some kind of m dash over m calculation. So I'd take this one and get m dash. So m dash equals yg, I'm going to square out the brackets just to keep it clear, x squared r squared divided by g. But we know that g here is this expression, so I can write y times gm over r squared times x squared r squared over g. What you'll notice there is the g's cancel out and the r's cancel out, so I end up with m times yx squared. Okay, and then if I just divide by the m dash over m equals yx squared, or as they've got it written down here, x squared y. Quite a tricky one I think, that one though. Okay, this is a planet of mass m and radius r, which rotates so rapidly that loose material only just remains on the equator. So if you imagine we're looking down from the north pole of this planet, okay, here's the equator, it's spinning so fast that the gravity only just about holds onto the material. This does have real applications when planets are being formed. If they rotate too fast, they sort of throw themselves apart. So we've got a gravity here which we know is gm over r squared is the force of attraction on these things, and that's just about enough to keep it in a circle, m omega squared r. Okay, I've chosen omega now because we want the period of rotation easier to go from omega to t than it is to go from the v squared over r equation. So if we start from that one, we cancel out the m's, the mass of the loose material, so that's gm over r cubed equals omega squared, gives us omega equals the square root of gm over r cubed, but we didn't want omega, we wanted t, so t equals 2 pi over omega equals 2 pi divided by omega, so we multiply by that expression, inverted r cubed over gm. They've used a big R, but nonetheless that gives us D. Okay, two identical spheres exert a gravitational force F on each other. What is the gravitational force between two spheres each of twice the radius? So we're starting off with two spheres of whatever radii they are with the force of F. Now we've got two more spheres, so this is M, and this is, each one's got twice the mass, but the separation of their centres is twice as big. So this is R. So if we took the force, for example, on this one, okay, it wouldn't matter which way around we did it, but that's G M over R squared. We've now got some more spheres which have got masses of 2m and 2m and a separation of 2r. So that's G times 2m times 2m over 2r all squared, and because it's a 2r all squared, of course, we've got a 4 on the bottom, so the 2 and the 2 cancel out with the 2 squared, and we end up back where we started with GMM over R squared. So actually the force is exactly the same. Okay, number 5. So a planet has half the radius of the Earth and a quarter of the Earth's mass. So again, gravity on the surface of the Earth is Gm over R squared. So this is G, a quarter of the mass, so M over 4 divided by half the radius, R over 2 squared. Again, that's Gm over 4, R squared over 4. They cancel out, and again we end up back where we started with the gravity being 10, the same as it is on the Earth. Okay, stating words Newton's law of gravitation. So the best way to do this, I think, is to say the force of attraction between two masses, nothing for that, is proportional to the product of their masses. Make sure you get that word in there, so it's the two masses multiplied together, and inversely proportional to the square of the separation of their centres. Don't put radius here, okay, I know you'll be thinking of GMM over R squared, but the separation of their centres is the best way to do it. If you really want to, you can write F equals GMM over R squared, but you've got to go through and annotate that to say that this is the mass of one object, the mass of the other object, the separation of their centres. Some of the earliest attempts to demonstrate the gravitation, to determine the gravitational constant, weighing the Earth, so by consideration of the gravitational force acting on a mass at the surface of the Earth regarded as a sphere R, show the mass of the Earth is given by this expression. Okay, so really this is just the gravitational force is mg, and that's equal to the gmm over R squared. Okay, so all you've got to do here is cancel out that m, cross multiply, so you get m equals g, this is, they're using a big R for the radius of the Earth squared over m. Sorry, beg your pardon, over g. Okay, make sure you write a capital R in there because you're not doing very much work there for your 2 marks, so try and do it properly. Okay, so now we've got to put some data into this. So in the following calculation, use these data. So you must do it this way, don't try and do it a different way. Calculate the mass of the moon. So we know that the gravity on the moon, let's call it Gm, equals G times the mass of the moon over the radius of the moon squared. If we just rearrange that, we get the mass of the moon equals G of the moon times the radius of the moon squared over big G. So this is 1.62 times 1.74 times 10 to the 6 divided by 6.67 times 10 to the minus 11, and that gives us the mass of the moon to be 7.35 times 10 to the 22 kilograms. Okay, if you've got to that, don't be too cocky and clever with yourself, because you've missed the second half of the question here. Express its mass as a percentage of the mass of the Earth. So that is, the mass of the moon is 7.35 times 10 to the 22 divided by the mass of the Earth, 6.00 times 10 to the 24 times 100. Okay, will give you 1.23%. Okay, you might remember the mass of the Earth is about 81 times the mass of the Moon. Okay, this is a really crucial question, so please make sure you can do this. T squared is proportional to r cubed. This is Kepler's law. So let's just draw ourselves a picture here to be clear. So here's the Sun. Here's some planet going around the Sun. Okay, this has got a mass of little m. The Sun has got a mass of big M. Okay, there's a force pulling it around, and that force is the force for circular motion. So the force of gravity is F equals G M over R squared equals M, and again, because we've got time in this, okay, it's much easier to use omega squared R. So that gives us omega squared equals G, the M's cancel out, the mass of the planet doesn't matter, so M over R cubed. But we also know T equals 2 pi over omega. So the easiest way to do this is to actually square that. T squared equals 4 pi squared over omega squared. And then we just take this omega squared expression here, put it in there, turn it upside down. So T squared is 4 pi squared times r cubed over gm. But all this part of this is a constant, so T squared is proportional to r cubed. Okay, so the Earth has a mean orbit of 1.5 times 10 to the 11. The Earth's year is 365 days long. The mean orbit of radius of Mercury is 5.79 times 10 to the 10. Calculate the length of Mercury's year. So what you need to do is to say T squared is proportional to r cubed, which means that T squared over r cubed is a constant for all the planets. So T squared for the Earth over r cubed for the Earth equals T squared for Mercury over r cubed for Mercury. We know the radius of Mercury, we want the year length, so the year length of Mercury, T squared Mercury, equals T squared of the Earth times the radius of Mercury cubed. Well, sorry, when I say the radius of Mercury, I mean the radius of Mercury's orbit over the radius of the Earth's orbit cubed. The easiest way to do this is to make the time of the Earth 1, so we'll do it as long as we're doing it in Earth years, that's okay. They've given us 365 days. I don't know, perhaps we should do it 365 days, keep them happy. So then we've just got 1.5 times 10 to the 11 over 5.79 times 10 to the 10. You can cube those separately or together. And if you do that in days, you'll get about 88 days for the year length of Mercury. I think 87.5. Same effort for Neptune. So we are definitely in years here, so 165 Earth years. So again, the same sort of principle here, really. T, the period of the Earth's orbit squared over the radius of the Earth's orbit cubed, equals the time for Neptune's orbit squared over the time for Neptune's orbit cubed. Sorry, the radius of Neptune's orbit cubed. So if we want to get the distances, Neptune's on the top, so the radius of Neptune's orbit cubed over the radius of the Earth's orbit cubed equals the time for Neptune's orbit squared over the time for the Earth's orbit squared. Well, that is, if we do it in years, 165 over 1 all squared. But this is the cubes, so if we take the cube root of both sides, the relative radius of the orbits is 165 squared cube root, okay, which gives you a ratio of about 30.